All right, similar reminders as last time, but I've shifted one thing and then just reminding about another. So um, this weekend with your groups, your algorithm choice is due Saturday night. Um, and that's, just gives me sort of a time to look over it. I mean, if it doesn't come in Saturday, I'm probably going to bug you and then, extend it or whatever. But that at least gives me time over the weekend to review those and then get me a jump start on providing any feedback. And for most people, they're just going to say, "Oh, it all looks good, looks good, looks good." So there's usually I don't have to provide a whole lot of feedback at this point. It's more the proposal where it's more interesting. And so that's April 13th when that is due. So these are both group assignments. Only one of your team members has to upload them. Otherwise, this weekend, there's the muddiest point. There's the concept check over this simulated annealing unit. But then the mini project for the simulated annealing unit, I thought it was a little too early to ask for it this weekend, given that things are about a lecture longer than I meant for them to take. So I shifted that to next weekend is when that mini project is due. Simulated annealing is not a difficult algorithm to implement. It would say it's probably simpler than the genetic algorithm you did in mini project one, just for those sort of considering it. And then I posted a announcement about this morning on Canvas. I also just as this reminder that the unit 8, which is on interactive particle systems and CAs, it's unlikely that we're going to cover it. If I trim my neural network unit a bit, then I think we could get it in. I just have to decide on what I want to compromise there. Assuming that it is unlikely, then I've left the concept check and the mini project available, but I've effectively made them optional by changing the drop policy from the syllabus. So the syllabus says you drop 3 concept checks and 5 mini projects, and I've implemented it on Canvas to say it actually drops 4 and 6. And so what that means is if you ignore Unit 8's assignments entirely, you'll get zeros for those. Those will get dropped, and you'll have 3 and 5 left over, which is what was originally in the syllabus. If those were topics that were of interest to you, or you wanted to make sure that you had an opportunity to look for credit towards the end of the semester, then I've left them available so that they're still there. But you're not, this additional drop here sort of suggests that if you have enough already, then it's not a big deal that we don't, cover that content. So that's how I'm trying to implement that. So those are the announcements. Any questions? Okay, so let's wrap up this simulated annealing stuff so we can start on swarm intelligence, the next unit. So from last time, we left off basically with this averaging result. This sort of relates to Borel's law of large numbers, where if you've got a function g of x and a sampling distribution, which I've said that it's the probability density function of this distribution I'm calling P of X, then if you sample points, X1, X2, X3, X4, all the way up to Xm, and then you run them through your function G, and then you calculate an arithmetic mean of the result, then as the number of samples goes to infinity, then this becomes a good estimator of this integral, which is the expected value of your function over that probability distribution, which is just, another way to say that is the integral of your function times your sampling distribution integrated over the whole space of X. And so, again, that's just like Borel's law of large numbers. This becomes the basis of Monte Carlo integration. So any integral that you want to take, then there is a way to sort of say, well, if I want to integrate under G, or if I want to integrate under F, some other function, then what can I do with G and P so that I have an effective way to just sample random points and then evaluate those points at the thing that I want to integrate, and then calculate an average, which I might need to scale. So I'll show an example of this on the next page, just letting this sit here. I might need to scale to get this estimate, but it basically at least provides me a way to turn a simple arithmetic operation into a approximator of a complex numerical operation. Because without this, then I have to do the numerics of this is I would have to cut this up, like do Riemann integration. I have to cut it up with little rectangles, which maybe looks fine if you're talking about if X is the real line. But let's say X is a 20-dimensional space, is like R20. Then it becomes very difficult to, I mean, if you think about it, even if X is two-dimensional, if this is a space that has an X and a Y, then and you've got this shape that you're trying to integrate under. Now you've got to put little little kind of square pencils underneath every point in that, in that shape. And then that is a huge space. And you've got to then approximate the height of each one of those pencils and then add them all up together. So it becomes a really ugly numerical operation to kind of do the way you'd learn to do integrals in high school or something like that. So this is suggesting, hey, you don't have to worry about going through the entire space. If it's a 2-dimensional, 4-dimensional, 18-dimensional space, as long as you have a way to sample points randomly through that space. So, if it's R20, then you're going to draw a random number for dimension 1, dimension 2, dimension 3, dimension 4, and so on. So you draw this joint distribution that gives you just a point in that 20-dimensional space. If you get enough of those points, then you just estimate this arithmetic mean, and you're going to get, with enough samples, an estimate of the integral underneath this integral here. So, like the example of this is the really simple case, is what if g of x is the identity function? So g of x is just equal to x. So g of x just maps x to this. So I guess I should have maybe drawn that the other direction. Maybe try that. If I'll erase, all right. Just make this x to g of x. I think that's a little more conventional. Well, that's not what I want. I'm just going to say g of x is equal to x. I'm not going to. So identity. All right. So if I've got this example here, where my g of x is this sort of trivial, it's the identity, and my sampling distribution are uniform. I'm just drawing uniformly from the continuous interval from 0 to 10, then this is my probability distribution. It's just going to be 1/10 the whole way between 0 and 10. So this is the Iverson bracket here. So this thing is 0 if the predicate's false and 1 if the predicate's true. And so this is just scaling 1/10 by 0 outside of 0 to 10 and 1 within 0 to 10. So that's just a uniform distribution between 0 and 10. And so if I take that and I plug that into the formula that I just had here, well, then this arithmetic mean turns into just the sample mean of my m numbers. Okay. And then so that goes to this integral, which is from 0 to 10. That's the beginning and end of my range here, and or my support. And then, that's this x, that's my g of x is just x. And then my probability distribution, my sampling distribution is just going to be 1/10 over this interval. So that pops out. So then it's just 1/10 of the integral of x from 0 to 10. Well, if you do that, x, the antiderivative of that is x squared over 2, evaluated at 10, that's 100 over 2, that's 50. 50 divided by 10 gives me 5, which is the mean of this distribution. So that makes sense to us, is that, if I take a sample mean of a bunch of samples from this distribution, if I get enough of them, I will get closer and closer to 5. That's all this is saying. But this expression tells us that we can generalize that to other functions. and other sampling distributions. So pretty much any integral that you want to solve, if you can put it into this form over here, where this is going to be how you're going to sample the points, and this is going to be, the additional function you've got there, then you have a way to do Monte Carlo integration, to do integration much, much, much simpler than trying to cut it up into little rectangles or trapezoids or whatever you want. That's the basic idea behind Monte Carlo integration. Okay, so questions about that so far before we get back to how this how this relates to Boltzmann and our sampling problem for simulated annealing. All right. So Metropolis, physical chemist from 1953, wanted to quickly solve an integral like this one. So for Metropolis, this is a important integral for physicists, basically. So this is the average value of a function which represents a macroscopic variable that you can experience, but you can think of this here as the instantaneous. So I could just maybe even, or maybe right here. So this is like instantaneous version of this macroscopic variable. So what I'm saying here is, like, there are certain microstates of physical matter, say microstates of the gas in this room. So you know every position and every momentum of every molecule of air in this room. Well, I might want to know what is the pressure for that microstate. So there's an instantaneous pressure. So at what pressure does this microstate put on other things in the room? And there is a function that I can plug in that says if you know all the positions and all the momentum, all the momenta of everything in this room, I can calculate the instantaneous pressure of that microstate. Now, I don't know, though, what microstate I have in this room. So I have to sort of say, well, what is the average pressure that I would feel from all possible microstates this room will be in? Well, I assume that this room is at equilibrium. So I'm assuming that the microstates are drawn from a Boltzmann distribution, because that's what the second law of thermodynamics says, that that basically we would expect the energy of those microstates to be consistent with a Boltzmann. So that's sort of this F down here. And so if I then integrate over all the microstates and I draw them from this energetic distribution, which allows me to map temperature to distributions of microstates, then that's going to allow me to take the average of instantaneous pressure, which gives me average pressure out here. And so that's going to give me like my P that I might put into an equation of state, like PV equals nRT. That's what that's what Metropolis and colleagues would like to do. This is an ugly integral because this down here is high dimensional. So the microstates of this room, that's all of the possible positions and all of the possible momenta of every molecule of air in this room. So even for a toy model, if you just sort of said, I have 100 molecules of air in a tiny box and I'd like to solve this, this is a pretty ugly integral to solve. And so that's what they wanted to say. Can we make this simpler by random sampling? And so that's the idea here. Now, what's the simplest way to do this? Well, when I look at this ugly thing that I want to solve, I can say, well, I know how to sample uniformly from a space. So if I've got 100 dimensions and I know sort of I could sort of put a uniform distribution on every one of those 100 distributions or 100 individual dimensions. And then I could sort of sample uniformly from the entire joint space of those 100 dimensions. I could do that, just sort of just sample every possible microstate uniformly. And that would be one way to do what we did up here for, use this guy up here for this problem down here. The problem with that, and so the idea here is I would sample a microstate, I would evaluate this product over it, and I would then do that for a zillion times. and then divide that by a zillion, and then I might then need to scale, kind of like I did here, by the volume of the room. So I'm going to get a this will that what I just described to you will be proportional to the integral I want. But then if I know how big the space is, and I know that I'm sampling uniformly from it, I could scale it to the actual solution that matches this integral here. But the problem with doing that is that if I think about this Boltzmann, many, many, many microstates will evaluate an f of x equal to around 0. So I'm going to uniformly sample without bias, just uniformly sample, and I'm going to get a bunch of microstates that are really high energy. And the Boltzmann, I'm going to plug them into my Boltzmann distribution, and it's going to say that's a super high energy microstate. At this temperature, it's never going to happen. So this is going to evaluate to 0. So your sum that you get up here, you're going to have a bunch of terms that evaluate to 0. And in order for you to really get a good estimate, you're going to need to draw lots and lots and lots and lots and lots and lots of points. And so it becomes computationally impractical to sample uniformly from these really high dimensional spaces where you're trying to integrate under something that really only has a bump in a very small area of that space. So I'm trying to integrate under a curve that doesn't exist everywhere, but I'm sampling uniformly everywhere just because that's the only thing that I know how to do. And so, and I don't know where exactly that distribution lives in order to sample from it. In other words, I don't have a way to sample from that distribution. That's kind of the key problem. That's what we're going to try to solve here. So, so that's the problem we're trying to solve. The solution that we're going to try to do is say, well, what if we could just sample from the Boltzmann? In that case, we don't have to do any scaling or whatever. We can just sample, pretend like rather than taking the uniform distribution as our sampling distribution, we're just going to try to sample microstates according to the Boltzmann. So those microstates that are very likely at our high temperature will be the microstates we sample more often. Those microstates that are very unlikely at this temperature, we won't sample them very often. And if we use that as our sampling distribution, then this thing will just naturally converge to this thing, and we won't even have to do any scaling like we would when we do uniform sampling. All right, questions about that so far before we dive deeper into that and then see how we sample from the Boltzmann? There's this basic idea of like, we want to use Monte Carlo integration, but sampling uniformly is just not practical. So we'd really like to sample from this distribution in order to really use the power of Monte Carlo integration. Okay. So that's all I'm saying here. So alternatively, if we sample from the Boltzmann directly, then this arithmetic sample mean will just go to exactly the integral we want. And we can use far fewer samples. And so we don't have to sample everywhere. We can just sample primarily the places where the temperature provided to us says that there's a high likelihood of microstates being populated. So that's what we're going to try to do here. So how do we do that? And that introduces the Metropolis algorithm. So the so-called Metropolis algorithm, which we're going to generalize into the Metropolis Hastings algorithm, it is pretty much the first Markov Chain Monte Carlo, MCMC, and it is also referred to as a Boltzmann sampler. So Boltzmann samplers are just anything that samples from the Boltzmann distribution. It's called a Boltzmann sampler. Okay, and so this was, came out in 1953, Boltzmann sampling. First step, you just choose a random initial microstate configuration. So it doesn't matter how you choose it. Just draw it uniformly if you want, whatever's easiest for you. Choose some initial configuration and say that's where my system's going to be in. 2, propose a random move, a move by random displacement. It also here doesn't really matter how you choose this displacement. A lot of times it's just a normal distribution. So you just draw, you say, I'm at this particular point and I want to move an average of 5 units away in my kind of, sort of in my, if I use a distance metric of like the Euclidean norm or something like that. So I want to just move, 5 units away and I have a certain variance. It doesn't really matter. You could use a uniform distribution, but you just propose some random move that hopefully it doesn't have any bias in it. So you don't want to like say like on average, I only ever move to the left. So it sort of should be a kind of a zero mean displacement. So like a normal distribution with some variance is a good thing, like a multivariate normal. So I could go anywhere. I could jump there, I could jump there, I could jump there. I start here at this random spot. And now I just need to evaluate, do I take that jump or do I ignore it and draw another? So step 3, if that jump, the proposed step, is at lower energy, I know my energy, I can evaluate it. And so, and I can also evaluate its energy. So I'm going to evaluate how energetic I am, how energetic it is. If it is downhill, if it's at a lower energy, then we just are going to take it. We're going to accept it with 100% probability. So downhill movements, you can't stop a ball from rolling downhill. It's going to do it. But then if at a higher energy, so if it looks like we're going uphill, well, a ball doesn't naturally roll uphill, but if you're kind of jiggling the bin that the ball is in, it will kind of go uphill a little bit. It won't just sit at the bottom. It'll roll a little bit up and whatever while it has energy. And that's what's happening to physical materials. And so this chair, me, you are being bombarded with molecules of air from outside our bodies, outside the chair, from in the room, that are at some ambient temperature. There's this heat bath that is sort of that we're kind of sitting in, and it's constantly hitting us with a little bit of randomness. Sometimes it's higher energy randomness than others. And so as we get those random transfers of momenta, then we can temporarily go up hills. And that's the same thing with microstates. Microstates, the physics is going to cause them to go as low as possible. But if you have some ambient temperature, you're going to get some random movements upwards. That's all we're simulating here, is that at some temperature, then, not what I meant to do, at some temperature, so there's our KT, then we're going to get a probability of being able to jump from E to E nu, even though E nu is higher than E. And so this is what we're going to evaluate. And that's going to be our probability of whether we go up. So we can just, draw, this is just going to be a number between 0 and 1. So how do you implement this in code? Well, how do you implement any, draw a random probability? You can just draw a random number uniformly distributed between 0 and 1. So in Microsoft Excel, you just say rand or whatever, or unith, maybe rand, I think. In MATLAB, in Python, there's a bunch of different ways to draw a random number between 0 and 1. Just draw a random number between 0 and 1. And if that number that you draw is less than this number, then you take the point. If it's greater than this number, you ignore the point. So otherwise, if you're ignoring it, you keep your original microstate, and then you go back to step 2. Or you keep the new point and then go back to step 2 and then try again. And so that here, if we replace this ugly thing here with a generic probability distribution where we're evaluating the probability distribution at our new point and then dividing it by the probability distribution, or I'll say the density function, at our old point, then this right here can be a direct replacement for that. And then now, instead of sampling from the Boltzmann, you can sample from any distribution. And that generic any distribution sampler is what we call the Metropolis Hastings algorithm. So Hastings just took the Metropolis algorithm in 1970 and just said, hey, I'm going to get rid of the Boltzmann and just put anything in there. And then I'll show that it also works for anything else. And that's today, whenever we talk about Boltzmann sampling, you typically say, sometimes people just say Metropolis algorithm, but it's more common to hear it referred to as the Metropolis Hastings. And that just means that you can generically sample from anything, not just the Boltzmann. All right, any questions about this flow, this algorithm? So it's just accepting and rejecting proposed movements and then using that to guide you through the space. Okay. So, like I said, Metropolis Hastings is one of the first MCMC, Monte Carlo Markov chain methods. So it is a Markov chain method because it has this Markovian property where your next state is sort of only dependent on your previous state. So in your previous state, there's a certain probability distribution of where you're going to go next. And that, that determines where you go next. And once you go there, then you forget about your last state. So there's no history. So it is a Markov chain. You're just jumping from point to point to point through this space. And it's a Monte Carlo method in that you're drawing these random points, but it's being driven by a Markov chain. So because of that, this is the samples that come out are not independent. So a random number generator that's one of its properties is you want points to be independent. If I ask Excel or MATLAB or Python for a list of 100 numbers, I don't want the first number to give me an ability to predict the second number any better than I could without knowing the first number. So that's what I mean by independence. With a Markov chain process, then the next point is very closely related to the previous point. They are so-called autocorrelated. So I know that if I'm at this point, then the next point is going to be nearby. It might be that over 1,000,000 points, if I marginalize all of those points, if I put them in a histogram, they're going to etch out whatever probability distribution I wanted. That's great. But from point to point to point, I can predict the next point very closely based on the previous point. So you lack independence. So that's the downside of using Markov chains to do Monte Carlo sampling. So that's why we have this term MCMC, is that it stresses that there is a lack of independence. But what do you get out of it? Well, what's cool about it is it's very easy to sample from high dimensional spaces. And there are additional benefits to that. It's very popular in Bayesian estimation. So in Bayesian estimation, very often what happens is you have a model of your system and you know how probabilities relate to each other. So you say that I know that I'm trying to estimate the distribution of a parameter. So that parameter could be, who likes ice cream or something like that. And all I know is that, someone sitting in this seat likes ice cream twice as much as that seat, and that person likes ice cream. It's like this is like a word problem from 4th grade or something like that. It's like maybe how the probabilities relate to each other, but you don't know what the probability distribution. You don't need to know the actual full probability distribution. You just need to know these relative relationships. In other words, you don't have to normalize. Because in Metropolis Hastings, that F function that you're sampling from, it doesn't have to be a probability density function. It just needs to be proportional to 1. In other words, it doesn't have to be normalized. So I could say that I want to sample from something that has a proportional probability of 1, 6, 7, 5, 2, 3. And all I'm saying is that this seat is I draw points from this seat 3 times as likely as that first seat that was a 1. So basically I could just say everybody's relative to that. Like I do want to draw for points from all of these seats, but because that seat is closest to the door, I'm going to say that people don't like to sit there. And so this seat is sort of in the middle. So it's 7 times as likely as that seat. Now I could solve I could say, okay, if I know that, that the likelihood of sitting in this seat is proportional to the distance from the door, I could go ahead and do the math and normalize these relationships and figure out what the denominator is in that probability distribution. But that gets really, really ugly when you get into these really complex spaces. Like you're trying to estimate where's the most likely place that coyotes are going to move in this space of, in Yellowstone National Park or something like that. And so that is kind of an ugly problem. But if I know the relationship that they're not very likely to go here, but they're more likely to go there, if I build up all these likelihoods and these relative likelihoods, then I don't have to normalize. I will get a distribution. Can say I want a distribution that's proportional to this. And it's just because of the magic of these likelihood ratios that show up inside Metropolis Hastings and many MCMCs that they basically divide out the effect of the normalization. So you don't need to normalize. Because normalizing a probability distribution is really, really computationally costly because it itself is an ugly integral. And we're trying to get rid of ugly integrals. So that's the big reason why these Markov chain Monte Carlos have become so popular in Bayesian estimation, is that when you're estimating a posterior distribution, given a prior distribution, you can sample from the posterior without having a proper prior. The prior doesn't have to be normalized. So that's why you see them a lot. Yeah, so hopefully that makes some sense. This is just kind of give you some background of where they come from and where this lack of dependence on that is. I'm not worried so much that you carry all of that away, but just to sort of say that there is a reason why these MCMCs are so popular for that. But we want to focus on simulated annealing. So before we get to that, any questions about that? So now we're going to use Metropolis Hastings in an optimization algorithm. That's where we're going next. But any questions on where we've come so far? Okay. So simulated annealing, Kirkpatrick et al., 1983. It's a science paper. It's not often that optimization algorithms get published in science. It's kind of weird. It is an application of Metropolis Hastings to optimization. And Kirkpatrick said you have four ingredients that you need for simulated annealing. The first one is basically a concise description of the system. This is just kind of an encoding of your parameter space. So this is an encoding of your decision variables. It's kind of like a genotype. Then you need a random generator of moves or rearrangements. So this could just a random number generator that can draw from a distribution with zero mean, basically. So this is commonly taken to just be a normal distribution with a variance that you get to choose. So there's going to be parameters here. So what we're going to get to here is that simulated annealing, extremely successful optimization algorithm, super easy to implement. However, it's not necessarily easy to use because it has a bunch of these parameters that you kind of have to tweak yourself. And so the simplicity and the potential for how well it works is kind of balanced out by the fact that you can't parallelize it. It only runs on one computer or one core, one thread. And it's got all these parameters that you might have to vary, just like in order to do real annealing in the physical world, you might have to do very different temperatures for one material than another. It's kind of a similar idea here. But the basic idea, concise description of the system, random generator removes, and then quantitative object functions or objective functions. So, that's you just have to evaluate whether each microstate is good or bad, whether the candidate solution is good or bad, and then a so-called annealing schedule of temperatures and lengths of time to stay at each temperature. And that's what we're gonna build out here next. And so basically this to choose your annealing schedule, this is kind of what I was hinting at a second ago. It's a lot of trial and error for a given problem. Now, nowadays, there are adaptive simulated annealing approaches that exist with dynamic schedules that try to choose these temperatures for you based on sort of sampling and modeling of the optimization objective as you walk through it. So basically, it's kind of like certain materials have different heat capacities, like, that water has a different heat capacity than air. So it's like if you try to heat water up, the temperature changes at a different rate than if you try to heat air up. And so optimization objectives have the same issues. That if you have a really flat optimization objective where like a whole bunch of candidate configurations are basically equivalent in fitness, if you want to call it that, if they're equally fit for your problem, then it's sort of hard to get a lot of changes in your system, even as you're increasing the temperature. So you get kind of it gets sort of stuck on these flat plateaus, the same way that certain materials, as you're trying to heat them up more and more, their temperatures aren't moving. So there's those sort of problems. But you can sort of try to estimate those properties, the kind of heat capacity of your optimization objective, and then use that to figure out, well, maybe I should increase the temperature now, maybe I should decrease it, and so on and so forth. So there are adaptive ways to do it. That's outside of the scope of this discussion. So we're just talking about the simple one where it's just got a static optimization schedule. Okay, so what does that look like? So for one, this came up in some of the muddiest points that I was answering this week, that like, how does this maximum entropy stuff really have to do with optimization? Well, and this is in the Kirkpatrick paper, is that they said, there's a bunch of these interesting insights about information from physics that through simulated annealing were imported into thinking about optimization and search. So when we're thinking about, like, if you're just at a particular point in the decision space, then you need to sort of say, well, how best should I move? And you could come up with all sorts of ways to decide whether to move uphill or downhill and how likely to move uphill and downhill and all of that. And by choosing the maximum entropy perturbations, you're basically saying this is the fairest way I can search this space. Any other way is searching in a way that reflects information that is coming from the programmer and not from the problem. And the programmer's biases might not be a good match for the optimization objectives. So you might say that, last week I solved an optimization problem where I would jump every like I'd always move 2 units in one direction for 3 times, and then I'd move 1 unit back, and that really worked very well for this particular optimization objective. So I'm going to try that with this new optimization problem that I'm doing this week. And it may not work that well for this week, because the reason it worked last week wasn't because it was a good general solution. It was because you happened to hit on something that matched the informational structure of the optimization objective you did for that problem. So if we want to come up with a way to search a space that is most generic, least unbiased, most general for any optimization objective, if we don't know anything else about that optimization objective, then there's a suggestion here that Boltzmann sampling is the fairest way for us to move through that space. And these ideas that came out, in these early 80s, now we see, as I've been trying to say, little residues of them all over machine learning and AI. Again, I keep bringing up softmax. Like, every one of the papers that my CS students write for me that I have to do edits of last minute because of some conference deadline, there's a softmax in every single one of those networks. And you just throw it in there, like softmax, and then you show me whatever vector you're doing the softmax of divided by some scalar. Well, that scalar that you're dividing by is temperature. And so, why softmax? Like, why is that the best distribution to blend all of the information that is accumulated through your neural network? This is the reason. It's like, because it's the least unbiased way to do that. So this is sort of applied to optimization, and that is applied to inference, but it's the same sort of idea. It's like importing this ideas. The physicists look at it as time goes on, you lose information about your history. And so you end up coming to equilibrium at a distribution that doesn't give you any insights into the past. It is fair. It is meritocracy. It is only based on the current information. And that's what we're sort of shooting for here. So Metropolis Hastings tries to use a fair sampling to provide the least biased stochastic local search for a given optimality budget. So that's the other cool thing about the Metropolis algorithm, is that it quantifies the kind of speed accuracy trade-off with an optimization budget. If you have a temperature, and so in Metropolis Hastings, this is going to be, we're just going to call this lambda, so that'll be our temperature. So we're not going to worry about scaling it or anything like that. I'll say temperature in simulated annealing. But the idea here is that this says that, if you crank this energy budget up, it allows you to do a lot more search, and that's going to maybe make you more accurate. But you're going to take, it's going to be a lot slower. So it gives you this one parameter that sort of allows you to manipulate the speed accuracy trade-off, and it captures that, in this nice clean way. Where if we talk about genetic algorithms and all the rest of those that we talked about so far, they just don't have these very interpretable ways of, you can talk about mutation, but what's the right mutation? What do you mutate? Here it's very clear. Like, we know how to mutate. We're going to mutate in the least biased way you can mutate. That's Boltzmann sampling, and we can adjust the kind of rate of mutation in this way where it's very clear that as the temperature goes down, the mutation, you kind of settle out in one area, so you can't do a lot of search. And then as the mutation rate goes up, then it allows you to search everywhere. So we had all these weird operators in GAs like crossover, that as long as you have diversity, crossover sort of allows you to search more widely. But once your diversity is purged, crossover doesn't really do a whole lot. And that's effectively an annealing schedule. That's effectively saying that you're going to have high temperatures early and low temperatures late. But this just makes it, I think, easier to interpret. So that's one of that's one of the reasons why this Boltzmann stuff was so kind of important. So how does this essay work? Well, so these are the kind of our mappings. So I mentioned the decision variable is this position of, I'm going to say position of an atom. So a decision variable in a vector is a position or position and momentum of an atom in a material, in a simulated material. Our candidate solution then, so our decision vector, is going to be the state of all atoms in the material. The fitness function, so the fitness, how fit we are, and in this case, we want to do minimization. That's going to be the energy of the material. So just like materials want to settle into low energy, we want to settle into minimal solutions. So if you want to do a maximization, you just put a negative in front of your optimization objectives. The initial candidate solution is just going to be random. And our selection, if we want to use kind of the terms coming from GAs, is going to be this acceptance function that I'm about to write on the next page. And this will be temperature dependent. And then finally, the process of generating new solutions will be the movement of atoms. So there's kind of random perturbations. And that's kind of up to you how you want to do that. So acceptance depends on temperature, and that temperature cools over time. That's the major function here. So let's see then how this plays out, what this basic algorithm looks like. So we're going to start here by looking at what the acceptance function looks like here. So that acceptance function is up here once that goes away. So this is acceptance probability. We've got, the idea here is you have a proposed new point, and you're sitting at this existing point X, and you're considering jumping to X new. So you have just drawn a random point from a zero mean distribution centered at, you add that onto your current point. That's how you get a random point away from that. So it's just a multivariate normal or whatever you want. You just jump away in a sort of an without a way that has zero mean. So, as long as you just have variance, but you're still centered on average, you don't move. And so that comes up to this proposed position X new. And so now we can evaluate the optimization objective at X new and at our existing X. We should probably already know this one. So we evaluate it there, we calculate this difference delta F. If delta F is less than 0, then we found a better solution. And that better solution is a downhill, and we always move downhill. So we're going to take it with probability 1. If delta F is greater than 0, so the otherwise case, then we're going uphill. And so uphill, we're going to plug it in to this. And now we know that that's that's the Boltzmann factor. It's the numerator of, well, you can think of it as it's a likelihood ratio of 2 Boltzmann probabilities. So that's where that comes from. That's why it's e to the 9 minus delta F. It wasn't chosen arbitrarily. They're trying to sample from the Boltzmann here. They're trying to sort of make the energy in your system converge to the Boltzmann, and where the relative to your energy function, which is your optimization objective. And so this hopefully will cause your, this here, I guess I'll add, well, hopefully, cause X to move to lowest energy and then you know then move randomly. I would say, well, I'll say on average, I'll say move to lowest energy on average. So the idea here is that you start at some arbitrary microstate, and then this process of effectively the Metropolis algorithm here is Metropolis Hastings is going to cause you to settle down, and then the residual movement will be based on temperature. So if we have lower temperatures, then you're going to hold closer to the minimum energy you found. If you have larger temperatures, you're going to move farther away. So that's our acceptance. The last thing that we have then is the annealing schedule. So the annealing schedule is just how we change this temperature over time. So we're going to stay at temperature lambda for beta, which is just a number of generations, when we use GA terms, newly tested states. So basically, you're waiting for thermal equilibrium. So the idea is you start at one state, and then you're said, okay, I'm going to take this many new samples. So I'm going to try here. Do I accept it? If I accept it, then I've got one new sample. I'll try here. Do I reject it? Okay, I'll try another one. Here, okay, I've got another one. This was lower. That's good. I'll take this one. So you do that until you hit, 10, 100, whatever this beta is set to. And then at that point, you decrease the temperature. So generically, you cool, but there's different ways you can cool. So one simple way to cool is just to use an affine function here, where you've got some initial temperature, lambda naught, and you subtract off based on t, where t is the time, like the number of generations or maybe the number of cooling steps that you've gone through your algorithm. And then alpha is the scalar, which is just gonna scale that down. How much temperature do I drop every one of those? So that's one way to do it. Alternatively, you could scale it this relaxation way here, where this way it sort of guarantees it kind of goes down to zero instead of tries to, eventually get negative. And so, and this is just the same sort of idea. I set alpha to be a value, in this case, to be less than 1. And then as t gets larger, then alpha t gets smaller and smaller and smaller. And so the lambda at time t, or at step t, is going to get lower and lower. So there's other ways you could do it as well. These are just two popular ways. And you possibly cool down to a desired final temperature. So you might, want to go all the way down to zero, which would be, total motion stops. That's like, absolute zero. But that's probably a little too far, right? Like at that point, if you have such a small search budget that you're not allowing it to search very far, and you have pretty high confidence that the kind of dips in your optimization objective are pretty high, then at some search budget, then you know that it's kind of like useless to try optimizing any further, and so you may as well stop. So this allows you to kind of stop sooner than waiting for things to freeze. That's kind of the idea here. So that's our annealing schedule. So any questions about that? Because that's basically simulated annealing, the key elements there. That's pretty much all you do in the algorithm. You draw a random point, then you perturb off that point. You see what probability is to take that point. You do that for beta generations. After beta generations, then you lower your temperature and then redo that. And you then go back and forth between those. So do this beta times, basically, lower the temperature, do this beta times, lower the temperature, and so on and so forth until you hit your final temperature or another convergence condition. And then whatever point you're left with, that is the solution to your problem. This does not give you a population of points. at every instant, it just gives you a single sample from hopefully your optimization objective. And so that's the kind of like, if you just let this thing go to a final temperature that was non-zero and you just let it run, it would become an MCMC sampler that would sort of always be giving you points near, hopefully, the lowest point of your optimization objective, sometimes a little higher on one side, sometimes a little higher on the other side. If you set this temperature really high and kept track of every point that comes out of it, it would etch out the histogram would sort of etch out your optimization objective, where it would hang around more often at lower energy spots, but then occasionally would get up to higher energy spots. And so if you looked at the density of the points that you got out of your sampler, then the high density points would be at lower energies and the low density points would be at higher energies. And that sort of density plot would look just like your optimization objective. Okay, so that's simulated annealing. Questions about that? Because I think that's all until we move to now the next slide is going to be me writing again, and we're going to go into distributed AI, totally new subject. Okay, so that was physics based. Now we're back to biology, and so this section, distributed AI, swarm intelligence. It's the basic things that I'm focusing on covering in this unit are so-called ant colony optimization, ACO, bacterial foraging optimization, BFO, and particle swarm optimization. PSO. I would say that PSO is probably um, the most popular of these three. Ant colony optimization is not quite as effective as it could be. It has some kind of niche applications. Bacterial foraging optimization is just not as well known, and so it doesn't have as many people implementing it. PSO is super well known, super old, super successful. It is a competitor with GAs, absolutely. So if something's not quite working well in your GA, you can use PSO as kind of a drop-in replacement. And all of these are like GAs. All of these are population-based optimizers. But although they have elements that seem, they do fit into evolutionary algorithms, even though they're not inspired by evolution per se. They're just evolutionary because you're reshaping a population based on relative success. And so they're still built as evolutionary algorithms, but there's no direct influence from genetics. Instead, the influence largely comes from behavior of group living organisms, thus swarm intelligence. All right, so I want to start with ACO. The ACO was originally called Ant System, but it just turns out that it didn't perform very well as Ant System. It was a cute idea, but it was like really outperformed by state-of-the-art numerical methods. And so they added things to it to make it perform better that aren't very ant-like. And then that's what became ant colony optimization. And so the idea behind ant colony optimization, this is an ant system, which is the precursor to ant colony optimization. So this is largely attributed to Marco Dorigo, still very influential. I think he's still editor-in-chief of the Swarm Intelligence Journal. There were several other people in his um, the kind of diaspora that has come out of his lab, postdocs and graduate students that have worked on that worked on Ant System and ACO as well. And so there are a bunch of other people here too, but a lot of people associate this with his lab and his influence. So the idea here is that this is a combinatorial optimizer. Now, there are now continuous variations. In fact, Georgios Fianakos, who now is working at Toyota Research and Development, he used to be faculty here at ASU. In his, I think, graduate work, he had to do counterexample generation for an automotive problem and decided to build his own continuous version of ACO to sort of search through different possible counterexamples that could break models of cars so that you could then present those counterexamples, say, hey, Toyota, it turns out that your cruise control, if people do this or they go across these particular types of hills, it goes outside of safety constraints as it tries to track the speed. Or if people are doing anti-lock braking, if they actually tap on the brakes in a particular way, it will disrupt the anti-lock brakes even though you put these protections in. And here I found this case. And so there are extensions of this back to the continuous, but we're going to stick sort of the simple combinatorial. And so the idea here is that decision variables come from discrete sets, not intervals. So what I mean by that is, I still have 100 decision variables in my decision vector, but in every dimension, rather than saying it could be anything from 0 to 1,000, I'm saying it can be only the whole numbers 1 through 1,000. So that's, I mean, it comes from a discrete set. And what that means is that we can easily set up paths. So I'm going to say we'll say that candidate solutions are paths through I don't like to call it decision space, but I'll just say candidate solutions are paths. That's all I'm going to say for now, and then I'll draw what I mean by that. So maybe I'll use the next page to draw this. I have a full. The idea here, the picture behind this is based on, and maybe I'll add this, based on kind of a cartoon version of pheromone trail laying by ants. And this will become clear when I draw this next diagram, but if you've ever seen a trail of ants on the ground, then the kind of basic picture of what's going on is that some of those ants found, say, a tasty morsel that they would like to bring other ants to then either take apart that tasty morsel where it is or even carry it back to the nest. But in order to get enough ants there to do that work, they lay a little trail of chemical breadcrumbs on the ground. And so other ants then can then follow those chemicals. So those other ants would be distributed around the whole world, but when they smell the trail in the ground, they follow the trail, and you get a trail of ants up to the food where they can then process the food and then bring it straight back home. They don't necessarily need the trail to find home. It's really just a recruitment mechanism to find the food. The trail might actually take them one way, and they might actually go a different way home. They don't necessarily have to go home along that, but usually the trails are led from the nest. So usually you're like, oh, this is really tasty. I'm going to go back to the nest, and then I'm either going to lay a trail on my way back to the nest, or I'm going to lay a trail when I go to the nest and then come back to the food. And so they typically to be laid on straight lines between the food and the nest, but the ants don't need them to navigate. They were able to find their way fine without the trail. And if they don't find any food, they'll go home without the trail. So it's a mistake to say that they're needed for navigation. But because they happen to be laid on these like straight line distances, a lot of people view them as ways of kind of solving these kind of traveling salesman problems where you're trying to look for the minimum path, the smallest or shortest path. But ants don't actually use them to solve shortest path problems. They use them for recruiting. But the picture that kind of Dorigo painted here is like, so let's say you've got a virtual nest of ants up here, and then we've got our decision variables. I'm going to just put down the side here, and so on. So I'll go all the way down to x to the n, or xn. So these are our decision variables. And because they're discrete, then each variable only has a discrete set of options. So the options for x1 might be, these points. So these are discrete options for x1 var. So the question is, I only get 1, 2, 3, 4, 5, 6, 7 ways, 7 options for choosing x1. Which one's best? Well, of course, I don't know which one's best without knowing what the other ones are. And they all have discrete options as well. So they're going to have a set of dots that may be more or less than the number of dots that x1 has. So x3 maybe has fewer. x4 maybe similar. And this goes all the way down to some final one here. So we've got all of our options. So these are options for each decision variable. So a candidate solution is a path through this maze from the nest to a food. So food. So I'll put just like food down here. And so the idea here is that the ants, let's say the ants are just using pheromone trails to find their way through all of the possible ways you could go from x1 to x2 to x3 to x4 to xn. We might want to reinforce, for example, the shortest path through this. I mentioned, again, real ants, they don't actually they can beeline, like real ants can do path integration. Some of them do it much better than humans do. So if you blindfold a human and you take them to that door and then you tell them to walk randomly and then walk in a straight line back to that door, most of the time the humans will just walk into the walls or something like that. But there are ants that's what they do. They live in deserts where they can't lay pheromone trails, and they walk in random paths and they go a straight line back. And so they're able to integrate in their head a home vector and do that. So that's, this reason why biologists don't really like this algorithm is like, it's a little silly and it's kind of, not very ant-like. But back when it was around, people were starting to think about ways in which ants could use pheromones. And around that time, this was a plausible way that ants could have used pheromones. And Dorigo just said, okay, we're going to build an optimizer based on ants. It was an optimizer based on a hypothesis about ants that is unfortunately turned into an ant optimizer when it isn't necessarily very ant-like. But that's the problem these hypothetical ants are trying to solve. So one path would be I go to the nest, I go here, 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 and then I get to the food. So that represents a decision vector that uses these different values of our decision variables. And another candidate solution would be I go here, 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 and then I get to my food. So then these points now become my candidate solution. And so paths through this are candidates. So what we're going to do is we're going to lay pheromone on each one of these nodes in this network. So we have to basically have memory elements that we need to instantiate. We need to say how much pheromone is on each one of these points at any time. And as ants try different candidate solutions, they will then have an opportunity to add pheromone to the nodes that they're using in their candidate solution. And that's going to accumulate over time. But then there's another process, and I'm going to write all this down, that is going to cause those pheromones to evaporate. So if no ant reinforces them, then eventually they don't get any pheromone. So initially, ants are just going to walk randomly through this matrix. But over time, they're going to be attracted to nodes that are smellier, that have more pheromone on them. And then that will cause them to converge to one, two, or three candidate solutions that seem to are the highest fitness. So how does that happen? So an ant goes through here. So I guess I'll just draw a an arbitrary path here. So we've got an ant. She goes through. She visits this one. She visits this one, and then she goes here. Maybe she goes over here, and then this one, and then finally hits the food. And so at that point, then we can evaluate how fit that solution is. So we can calculate fitness of path. So I could call that, it looks like I call it capital F. So we'll call this F, and we can imagine that that whole path here, I'm going to say this is xj, and I'll put a little vector over it here. So this is the path of ant j. Okay. So that's not referring to vector or variable j, but saying ant j has walked through this. And so there's ant j, this vector that could be broken down into these dimensions. And so this one path represents x1 at that value, x2 at that value, x3 at that value, x4 at that value, xn at that value. All those are packaged into this one xj. So I can just call this xj, up and down here. All right, questions about that so far? All right, so we're going to evaluate this fitness, and then we're going to add and I think I'll call it delta, maybe. Well, I'm just going to keep it simple. I'm going to say add Q, which is a hyperparameter, divided by F xj vector to every node along xj path. I'll try to write that out so it's a little clearer. xj path. All right, so we're just going to add pheromone to each one of these nodes. So if so in this case, I guess I should emphasize here, we're we're trying to minimize. So this is minimization case. And you can think of F then as the length of the path. It's like a generalized length. So if it was a really long path, we're not going to add much pheromone. If it's a really short path, we're going to add more pheromone. So if it's a high value, then the Q amount of pheromone I have available to add gets divided down. If it's a low value, it doesn't get divided out as much. So you add more pheromone to smaller values because we're minimizing. So then we then decrease all, old concentrations by a fraction. and this is evaporation. And so we can write that sort of say like, well, okay, so the what happens to the concentration at each one of these? So we're going to say that each node has got a concentration. So this is concentration I, comma D. And so this is the concentration at variable I for value D. And so that concentration I, D, this is the prime is the new version. So at the end of a generation of this, at the end of evaluating this for every one of these, then the new concentration is going to be some decay rate, 1 minus rho, of the old concentration, plus the sum of j equals 1 to my m ants of each one of these delta ci d for ant j. I'll put ant j in parentheses here, where this is this thing right here. And so we've got decay, evaporation, and this here is reinforcement. And of course, I haven't shown you the other half of this, how the ants respond to that. But this is just when every ant runs through, this is what we do. So what we'll pick up on next time is then when a new ant leaves, she is going to look at the probability at each one of these nodes. So when she comes out of here, she's going to look at all of her options, and there's going to be concentrations at each one of these nodes. And she's basically going to do, she didn't do a soft min, but she could basically do something like a soft min. She's going to do proportionate selection across these to decide how likely it is for her to go to each one of these nodes. And then she's going to do that over and over and over. And then that is going to cause future ants to be more likely to take well-reinforced paths, further adding well-reinforcements so that you end up getting a convergence of a bunch of ants on a particularly good path. That's where we'll pick up next. Thanks.